Thank you. My name is Dennis. I work at EPFL, the place where Scala was invented. So I'm doing my PhD there on this project called Scala Native. So the main idea and main vision behind Scala Native is to completely cut out the VM part of Scala that we have today. As you might know, Scala today is compiled in two kind of steps. So first we compile to JVM bytecode, and then JVM runs this bytecode. But you can't really do it separately, so you really have to have a JVM on the target machine, which is not always practical for some applications. Like, for example, for mobile phones, there is no JVM for iOS, because on iOS you could not do JIT. In some kind of embedded environments, JVM is really not practical. And overall, in many, many different use cases, you would really not want to have a fat, resource-hungry VM, but instead just have an application pre-compiled to native code. And that's what Scala Native is all about. It's about removing the VM from Scala as we have today. My talk today is going to use a 0.1 release of Scala Native. It hasn't been announced yet, but we've published everything. So it just essentially everything you see here is using artifacts from Maven Central, so you can just reproduce it as is. And I'll probably post the code that I will get in the end on Twitter. So basically, what you see today is Scala Native 0.1 to be announced the next few days. OK, so the whole thing that I'm going to do today is completely live and almost not scripted. So essentially, the way you start the Scala Native project is completely the same as you would do on JVM. You would make a build file for SBT. So we do a build with SBT. I'm going to code in Vim, so I really hope there are no Emacs people in this room. Yeah. So we make a build file. So in fact, we need actually two files here. We need to tell SBT that we are going to use Scala Native, which is just a plugin for SBT. It's really not different from any other plugin. So we do add SBT plugin or Scala Native. SBT Scala Native 0.10. Yay, production ready. OK, so here we are. We need to enable plugins, Scala Native plugin, and we need Scala version, because we don't want to use 2.10, which is a default Scala version on SBT still. And now we start SBT. It will probably take some time for it to resolve everything. I hope I have Scala Native itself in cache, so it will not take too much time. Oh, that was fast. OK. Yeah, exactly. Lies. So the way you interact with SBT with Scala Native is completely the same as you would do it normally for JVM. When you want to run your app, you just say run. There is really nothing more apart from actually writing some code to compile. Yeah, we do need to compile some code, right? So our application is going to be a single file Scala app. So we start with just standard hello ScalaMatsuri line. OK. There's nothing special, just to test that our build actually works. Oh, yeah, help. Sorry. OK. OK, nice. It's actually run, so let's change it to the correct one. As you can see, the whole thing is actually surprisingly fast, given that it compiles all of your code to LLVM every time you run it. So if you look at all these comments on the right, it's basically everything that we go through, all of the pains and difficulties we go through to get our code from nice high-level language to very low-level language to native code. And it really takes just a bit of your time, so it's like 1.5 seconds for this program. And yeah, it was hard to get there. But so we want to make an app. We want to make a graphical app. So usually what you would do in this case, you would use a framework that was made for this. And there is a very, very nice framework for this called SDL, which is short for Simple Direct Media Layer. It's a very simple, very cross-platform library in C. we're going to call it, we're going to use its APIs in Scala, and we're going to do our game based on this framework. So, the way SDL works, you first need to initialize it, then you create a window, and then you do your stuff in a window. But to call SDL, we cannot really use normal Scala features because there is no normal Scala feature to call C code, right? It's like not possible. There is GNI, of course, but it's not really quite the same because GNI isn't really a foreign function interface. It's like an interface from C to call JVM mostly, not the other way around. So to build extensions for JVM. But in Scala Native, we really don't want to write C code. We want to write Scala code. And we just want to depend on C libraries. And to do that, we have a small, tiny language extension that lets us effortlessly call C code. And it's really tiny, like seriously. So to enable this thing, we need to import it from scalanative.native. And we need to define something called extern object. So extern object is a special thing which says everything in this object is not really Scala code, but it's more like an interface to C code. We usually use extern objects to define signatures for C functions, but also we use it to define type aliases for types which were defined in C code, like, for example, structs. So to create an app in SDL, we need to call SDL init. So SDL init is a function that takes some flags that tells us what kind of features do we want. It's unsigned int, if I remember correctly, and it doesn't return anything. And right-hand side is extern because we don't provide an implementation. We look it up through a C library solution. Then we also want to create a window. So create window takes quite a few options, so I'll just look it up. Yeah, it's title, which is C string. It has coordinates, which tell us where this window is. It has width. It has height. It has some flags probably too. OK, that's good. And now, apart from window, we also need something called renderer. So renderer is an API that lets us draw on a screen. It lets us invoke calls like place a rectangle here, or clear screen, or update screen, and so on and so forth. So we need to, and actually, by the way, create window gives us a pointer to window. So now we also need to create renderer. It takes some stuff. Create renderer, like, yeah, it needs a window. It needs an index, and it needs flags too. OK, and it gives us renderer. We don't really know what renderer and window are. We just define them as some C struct without any fields. It can have some fields, but we don't really care about it because we're not going to look at its internal data representation. So cstruct0 is essentially a special type that says this is some C type, which we don't really care about, like opaque thing. We will not going to look at its contents. We just need to know it's like it's out there. So it's a pointer to something. But we just want a nice type aliases to kind of make it clear in the code. OK, so now we need to call those guys. So we init with init video. Init video is a constant defined somewhere, so we just look it up. And all of these guys are we going to use as constants for flags parameter. So flags is basically what kind of window do you want, what kind of renderer do you want. Do you want your renderer to be synced to the screen, or do you want your renderer to be completely unsafe? It's really kind of like an options, basically. So we also want a window. Create window. We need to give it a name. By the way, I haven't told you this, but we are making a snake game. Yeah. So we're going to say we want a snake window at 0, 0, 800 by 800 should be enough. And we want window to be actually visible, so we pass window shown over there. And we also need a renderer, which takes a window, which takes index, which we don't care about, and takes vsync flag because we want our image to be nice and synced. And we can actually try to run it now. Yeah, of course. Render. Okay, yeah, right. That's true. Not reader, renderer. Renderer. Okay. Now we need to import this object because this is how Scala works. Cool. And we also forgot to give this another extra annotation which says, I want to link with this library, because otherwise it doesn't know where to find it and what's this library called. So we say link with SDL2, and it will do its magical thing and find it somewhere. Okay, so there was a window just for a second. It was not visible actually because essentially our application just creates window and then like quit. It's like we don't handle anything, we don't do any extra logic. So next step we want to do is we want to actually window to stay on the screen, which is probably like not too much to ask, you know. So this stuff we've already done now. We're gonna just put it into helper function, which just initializes all the things we care about. And we call it init because that's what it does. Okay, and we call this function. Apart from init, we need to actually do the work that application is supposed to do, and it's like to be a game. And essentially what we need here is an event loop. We need to handle events that SDL tells us. Events are like things like a user pressed a button, a user moved a mouse, a user closed the application, etc., etc. SDL supports a large spectrum of events. We're not going to look at all of them. We're just going to care about a few. So to do an event loop in SDL, you just essentially do a while loop that calls something called SDL poll event. So SDL poll event is a function that takes an event, and then because it's a C API, it just stores its result in there, like in place. So we need to allocate it somewhere. So event, also we need to define events. We haven't defined them yet. So SDL events are untyped union of different types, but essentially it's a tag which is a number that says what kind of event it is, and then it's like some data which is different per different type of an event. Like for example, keyboard event might store key code, mouse event might store a mouse position in this data. So to do a union in Scala Native, we just basically do a least common denominator of all the possible options. So for event loop, it's uint, yeah, of course. And then we have some extra data which we don't care about, like 60 bytes of stuff. And this 60 bytes are going to represent different data based on event type. And this underscore 60 is a number. We don't really have type level numbers in Scala yet. So we use an encoding like this. Not digit, not 6, not 0. And essentially this gives us a number. And this is essentially just a type level representation. You might have seen different encodings, like I think in Shapeless or cats they have 0 and suck, and you can like get 60 by calling suck of 0. But typically in this kind of environments you get large numbers, like I want 128 bytes. You don't really want to type this kind of large numbers, so we have slightly different encoding that kind of optimizes for bigger numbers. And we want poll event. Poll event is an event that gives us the event, and it stores it in place. So we'll also need to allocate it somewhere. So SDL doesn't allocate it for us. Okay, and this one is, synced. Okay. So now we are almost ready to handle our first event. But another thing we need to do, we need to put events somewhere. So in C, the way you allocate stuff is one of the two ways. So first, you can call malloc, or you can stack allocate. So in C, stack allocation is like a built-in kind of syntax. In Scala, there is no built-in syntax for this, so we have a helper function that does the same thing. So what we do, we say event is stack allocated event. That's it. it will find a place on a stack that has enough memory for event to be stored, and it will free it as soon as we exit the game loop. And now here we also, by the way, need to do this because poll is async. Okay. And now inside the loop, so we know that SDL event returned non-zero, so it actually stored something inside. So we need to dispatch on a type of the event. So type is the first field. And to make it a bit nicer, so we define type as cstruct2, by the way, because it has 2 fields. To access fields in Scala Native, so if you have pointer to struct n with n fields, when you say pointer._number, like _1, for example, in this case, it will give us a pointer to the first field. And then we can dereference this pointer to get the actual value. So we can do this, basically. And then we can say, for example, if there's a quit event, then we just return from the game loop, and otherwise we don't do anything. And this should keep our window open until the user actually closes it.
I have a question, though. Should that be called in the while loop SDL full event?
Yeah, exactly. You're correct. OK, I think we're good. Let's say not SDL event, but just event. Match. Yeah. And we need to define SDL queued, I think, too. Queued event, yes. OK. This should be enough. Yay, we have a window and it doesn't even close. Woohoo! Okay, yeah. So, and now we can even close it, yeah? It's amazing. And by the way, if we remove this line, it will just freeze and just not do anything, and it will consume all events until we force queue it. So basically, we should, this one is a must in any app that pretends to be an app. Okay, so now we have an actual window. We want to do something with this window. We want to paint, we want to animate, we want to have fun, right? And before we go there, so essentially our event loop essentially will do stuff in a kind of async way. And it's really nice. Poll event, like if it doesn't have events at the moment, it just returns. So this is why we have while true. And we would also probably want not to poll for events like millions times per second because there is no good reason. So we can say delay here for like, so how many frames per second are enough for everyone? Like 12? Yeah, for this game, probably 12 is more than enough. And delay is just another helper function in SDL. So it takes milliseconds, which is probably unit, of course. So yeah, this gives us unit. OK, cool. So now we poll a bit less. And now it's going to be helpful because so now we're going to start doing stuff. So in this game loop, we don't really want to put all of our code in there. It's just going to be a dispatch place that kind of calls other handlers. Like, for example, we can do an event handler for you need to draw, like draw event. We can do an event handler for we need to handle key or we need to do something like this. So basically, we put all of our actual logic outside. So the first event we're going to handle is draw. Okay, so draw. So what it has to do? It has to present something, and we are making a game of snake. So have anyone ever seen Game of Snake before? Okay, so it's like the simple game where you have a snake that eats an apple, and it grows if it eats an apple, and it fails if it hits a wall or if it hits itself. So we need a snake. So we are sort of like a Scala-ish functionalish language. So let's make it a list, an immutable list. And we'll need some kind of list of something. And in the case of snake, it's like it has this kind of segments, which corresponds to like body parts. It has a head, it has body parts, and has a tail. Essentially, all of those are just screen coordinates. So we say there is a thing called point, which is just a case class that has x and y. We can do two simple operations with points. We can add them. Another. This will give us a new point with x plus other x and y plus other y. And we can subtract them, which is the same thing, only with minus. Okay. No. Okay. Okay. So now the snake itself is going to be our main game state. So, and the snake is just a list of points. So we start with a snake at some position in it. So we need to create the default snake state. And it's going to be a point of, I don't know, 10 to point 9, 10 to point 8, 10 to point 7, 10. So the first coordinate is x and y, like we've seen before, and it's just a list. So we have a data structure. Let's check it compiles still. Yeah, it's still good. So now we need to draw it. So the way we're going to draw it is just a very, very simple thing. We're going to draw a square for every single part of the snake. The squares are going to be green because snakes are green sometimes. So we need to draw a snake here. And we need to draw present in the end. And we need to clear the screen before because there was other stuff we've had before. And we need to set color that we want to clean it with. And it's going to be black. We're going to use a black background. And black in RGB, that's what I'm doing right now, is 0, 0, 0. Okay. So now we need to draw a snake. We need to learn how to present stuff once we are done. And we need to know how to clear stuff somehow. And we need to be able to set current color, which will be our GB. Okay. So all of these draw functions, apart from draw snake, are just nice aliases to SDL render functions. SDL render functions take a renderer, which is like the main state of where we are rendering stuff to, and it changes it. So essentially, we just create some aliases to make it a bit easier to write. So essentially, we're going to use these 4 render functions as our foundation for our snake game. So it's just 4 functions. So first one clears the screen with current color. Set render color sets current draw color. Fill rect just draws a simple square on the screen. And present just syncs renderer with a window. Okay. And here we have also a type which we haven't defined yet, which is rectangle. And it will be a C struct with 4 elements, and they are all ints. And they are x, y, width, height. Yeah, okay. So draw color will call SDL set draw color. In draw color, a double assigned. Oh, yeah, thanks. Good point. Okay, and then it takes renderer, RGB, and alpha. We don't care about alpha, so it's always 0 in our case. Clear is SDL, render clear, render clear. And draw present is STL, render present. Okay. So draw a snake, we're going to just draw a bunch of rectangles on the screen. And to be more precise, we're actually going to draw just squares. So it would be nice to have a draw square helper. So squares are going to be all the same size, so they don't need width and height. They just need a position in our coordinate system. And to draw a square, we're going to use render fill rect. This one. Text renderer and text rect. And that one is, again, has to be defined by us, allocated by us somewhere else. We're going to use stackalloc again. And of rect. And we're going to set all the fields to values we care about. So it's XY. Okay. And this should render a square. And to draw a snake, what we do, we know that snakes has at least 4 segments. So we can do a really unsafe otherwise thing. We can say head, second, rest. And this will never fail because we know snake starts with 4. What? It's fine. Yeah. And so first we draw a head. So we draw a head with slightly lighter color to make it clear where it is because it has 2 ends. And essentially we do something like 150. Should be light green. And then we draw a square. Add head. We can actually take a point here. Okay, so now we draw a head, and we also need to draw the rest. And for the rest, we're going to use a slightly different color because we can. It's going to be a dark green. And then we actually don't care about, we just do rest for each because it's a list. And we draw a draw a square for each one of them. Yeah, it's this easy. Illegal start of simple expression. That's helpful. Yeah, thanks. So it's almost what we want, but not quite. Yes, that's correct. That's what it is. So we have a tiled thing, right? So it's, you're absolutely right. Yay, it's almost right. I think we initialized it incorrectly. Where is init? Okay, yeah, we dropped one coordinate here, so it was. Okay, that was easy. Okay, so now we have a snake. Now we would like it to move, right? It's really not a game yet because it's like, oh my god, it's like, oh my god. How much time it took together though, but okay, so we would like to animate. And to animate, we just know once every frame, we need to update our game state, which is our snake, to change from current state to some other state. In our case, right now, the whole game state is just one mutable variable snake, which points to a mutable list. So we do a new event handler called onIdle, and it's going to happen approximately 12 frames per second. And here we're going to actually do animation. So to animate the game, so essentially the mechanic of the game, if we don't do anything, it just moves in its default direction. And default direction is defined by where the snake looks at. So if it's in our current example case, it looks to the right, if I'm correct, yes. And it will, if we don't touch the keyboard, the expected behavior, it should just slowly advance 1 pixel at a time to the right. To implement that, we just need to figure out the direction first. So direction is essentially a vector from a second to head. and then we increase our head. We move our head by direction, by head plus direction. And move, updates the snake, and it essentially takes a position and new position. And new position becomes a new head, and we discard the tail, and in Scala it's like this, as simple as that. Like a start of simple expression. Yes, this one. Not quite correct. Why is it not correct? Because head minus second not. Yay, it moves. Okay. So now it even moves. So we are like almost done, guys. It's like another 2 hours and it will be like a game, right? Yeah. Okay. So now we have like two key game mechanic parts. So first, we need to handle keyboard. We need to know when user presses one of the direction keys on the keyboard, like up, left, right, and bottom. And we need to move in that direction instead of default direction if one of the keys is pressed. To handle the event, we need to do something here. So essentially for keyboard, we get another event, which is a keyboard event. And a keyboard event is a bit more involved than the events we've seen so far, because it actually has some state we care about. And more specifically, we care about the keys that user pressed. And we care about these guys too. So these are just constants for different keys and for, Okay, so this we don't need. And we also need key pressed event, which is not here. That's weird. Okay, let's reverse engineer what's the number for key event. That's going to be easy. So every time we don't handle the event, we just print whatever key code it has. Code. Okay, so we press the key a few times, and it's gonna. Oh my god. Okay. Okay, let's do it real time. So, by the way, the things that we are doing is actually SBT generates a native binary that I'm gonna launch right now, and it will give us so it's either 768 or 769. Probably. So one is up, another is down. That's good. This is basically this guys. I'm sorry, I wasted your time. But you see, it's super easy to reverse engineer it. Are the guys which are accidentally removed. So, and they're actually exactly what we need. So we handle those two events. This one we don't do anything. So for this one, we actually need to read up some state from the event. And this state is encoded in this a bit long type, which is keyboard event. It has really a bunch of stuff we really don't care about. The only thing we actually care about is this last field, which is called key theme. And key theme is a struct which contains information about the keys that was either pressed down or up. And in key theme, we care only about key code. So what we care about is actually event._8._2. And this is going to give us a value. And as we know here, event is pointer of event and not pointer of keyboard event. So let's just do unsafe cast here. So that's perfectly fine. It's absolutely fine. Yes, exactly. So we _8_3, what is that? _8_2, and then we dereference it. Of course, we can, if it wasn't a live demo, I would have created a nice helper function that makes us hide all the underscore numbers. But I have only 5 minutes left. Oh my god. No. Okay, let's speed it up a bit. Okay, that's essentially, this is going to give us a value, and we need, so this is basically key. And essentially, we would like, on idle, we need to know what keys are pressed, so we just store them in a set. Okay, and pressed is going to be a bit of more state. Normal Scala set, empty of key int. Okay. Okay. What's up, man? Okay. We don't have mutable. Scala collection mutable. Okay, so we don't do anything with this pressed state. So now in on idle, we need to actually take it into account. And the way we do it, we just check if a key that we care about, like up, down, left, right, is in this pressed state set. And we just do actual user direction equals if pressed contains right key, left key, up key. Okay. So we just do an if, else, if, else, if. It's very simple. Right key, we go right. Else if pressed contains left key, we go left. Else if pressed contains right. Up key, we go up. Else if pressed contains down key, we go down. Okay, and otherwise we just do a default direction if nothing is pressed. We need to define these ups and downs. They're all directions, and their type is point, so up is going to be 0, -1, 0, 1. Left is -1, 0. And right is 1, 0. Okay. That's good. And it might even work now. Okay. Still doesn't work? Exactly, correct. Oopsie daisy. Hey, it moves. Okay, so now, last thing, we need to actually fail sometimes, and we need to win sometimes, right? So we can move, but it's not a game still. We need to figure out what conditions are fail conditions and what conditions are win conditions. So for fail conditions, it's actually very simple. We can go out of bounds of the map. So it means our next position is 0 or less on either coordinates, or it's actually on the other side, which is 40 or more. So we need to check basically here. So this is only fine if everything went well. And if, for example, new pos.x is less than 0, or new pos.y is less than 0, or new pos.x is greater than 39, or new pos.y greater than 39, then we need to fail somehow. So we do game over. And game over is over equals true. And print line, you failed, sorry. Okay. Okay. So an over is another piece of state we need to put somewhere, so we put it here. And we don't do anything once game is over, so on idle is only called if it's not over, if not always lost. Okay. Yay, we lost. You failed me, yeah. Sorry. Okay, so another fail condition if we hit ourselves, because as soon as when snake gets longer, we can start being able to hit ourselves. It can happen yet. It's really hard to make it happen like right now, but we just need to handle it. And this is going to be like super simple because snake is a list of positions, and we have a position. We do this. Yay, we did it. We can't really go there yet because our snakes are too short. So next thing we need to do is we need to introduce a way to win, right? So we can fail, but we cannot win. So we need an apple. An apple is another kind of piece of game state, and it's a point which is a location that we can eat. And this apple has to appear randomly in different locations to make this game interesting. So in it, we say apple equals new apple. And this has to generate random apple. To generate random numbers in Scala, we are accustomed to using Java till random, so let's just do that. And essentially, it can be the case that we'll make a position that is actually not really to our liking, and more specifically, it can be on the snake. We don't want that. So we try a few times until we get the good one. And this is going to be red next int. So it will give us a number from 0 to 40. And we do this while snake exists, point, and we return this point. And we also need to render this, draw apple. So apples are red, so let's do that. So, so to draw an apple, we need to pick a different color, which is going to be red. Yeah. And we're going to draw a square at apple position. And we put it here. Oops, waited. So we did the bug somewhere in an error checking. If snake exists, we probably accidentally this doesn't.
Isn't that you failed the game?
Yeah, but it was in the middle of a screen, so I couldn't have failed at the time. It's really how did that happen? Okay, now it works. Okay, so we have a bug somewhere, so that's fine. This happens. So now. But Apple was there, so it's and now another interesting part of game mechanic is we need to be able to eat an apple, and this happens when we move and our new position is an apple position. In that case, we have to increase our length. Else, if apple equals new position, we do this. So we keep all of the previous snake. And we add one more.
I'm sure that
5 more minutes. I think 5 more minutes, and it's basically, yeah, and it's there. It's almost there. We have a bug somewhere. Okay. But essentially, the whole point here is, so right now, when we eat an apple, we add one more point. And it's actually done as soon as we find that bug. Yeah, it's basically done. Yeah, we can win, right? Okay, guys, so that was it. Thanks.
Thank you. And time is over, so if you have some questions, please talk him later, please.
That's fine.
Thank you very much.
Thank you very much.